So let's see. We're going to go have our problem session. They'll be in room 90 at least to start until there is a training that I think many graduate students have to make. Some of the first years have been very close to that takes over the second half of the semester. So we'll move into another room then, but we'll start up here. We had, as I said, we talked a little bit about the timing for office hours. Actually, that slot that we decided probably wouldn't be the best for us. So, and then 11 o'clock, there was maybe one person had a conflict on Monday. Anyone else have conflict? So we'll do that still, and then if there'll be other times, because it's not always available. So. All right. Very nice. So let's quickly review where we were and try to get solidify some of these concepts that we're reviewing. So we're talking about the quantum electromagnetic field. So we're reminding ourselves of sort of the very basics of how we describe the quantum field. And the key concept here is to think about the field as a collection of normal modes. And that means we have a kind of generalized Fourier decomposition of the field into these normal modes with amplitudes. So the modes here are defined by certain spatial fields I put in as you might have some strength that we want to put in to give this the units of electric field. And then through each normal mode, there is some amplitude in that mode, which is time dependent. Okay? So each normal mode is then reduced to, once we know what the modes are, the dynamics of the field are described by the time evolution of the amplitude in each mode. Okay? And those are complex amplitudes representing a magnitude in phase, or equivalently two quadratures, which we wrote as those real and imaginary parts of the complex amplitude. Okay? And so each one of those amplitudes goes around some way, and that tells me what the field is doing. That's a classical description. If we have a free field, meaning that the field is not interacting with sources of the field, charges, then the solution is simple. It's the solution to the free Maxwell's equations in the absence of sources. And the solution will then just be that each one of these amplitudes evolves like a simple harmonic oscillator complex amplitude. Okay? And that's what makes it a normal mode, is that it has this defined time dependence. I mean, you know that from your standard problems that you solve the mechanics of coupled masses on springs. You can write that whole collection in terms of a collection, instead of thinking about the individual masses of springs, you think about the normal modes. And then there's a time to each one, their canonical coordinates, etc., associated with each of those things. Pity we don't teach that as much anymore. Anyway, right, now just a quick aside here. We can also include in the description of this classical field randomness in thinking about these amplitudes as classical stochastic variables for which we don't have complete description and we would assign some probability distribution to what those amplitudes are, okay? That's still what we would call a classical field. But it's a classical field for which we don't have complete information. And so we would put some probability associated with those guys, right? So in that case, we would describe some, glad I got more chalk. We define some probability distribution, so we can have a stochastic field with some probability distribution associated with all those amplitudes. Okay? So this would be some probability distribution. Right, okay, so again, just in terms of jargon that we use, when we talk about the complex amplitude, again, we can think about it as having a magnitude and a phase, or a real and imaginary part. And those real and imaginary parts are what we call the quadratures. Okay? So they're called quadratures because they represent the, if you have any function that is oscillating at a single frequency, it can always be expressed, always, as some amount of cosine and some amount of sine. And those two things are 90 degrees out of phase. They are in quadrature because they're 90 degrees out of phase. That's why it's called a quadrant. That's where the term comes from. The quadratures tell me about how much of this thing is oscillating like cosine and how much is oscillating like sine, with some fixed definition of what zero phase means. Okay, so it's always relative to some reference that we're calling zero. Okay. Now, when we looked at this last time as a classical simple harmonic oscillator, we thought about it as a mass on a spring, but we don't have to think about that. In this case, these harmonic oscillators are not associated with the mass of any, the motion of some massive particle. It is the amplitude of this normal mode. Okay, so these x and p's aren't the position and momentum of a particle. Okay, because as we were saying here, when we quantize this, and now we have our quantum description. So now we have quantum quadratures. And the quantum quadratures, if they're the x and p associated with the same mode, they don't commute. If they're associated with different modes, they do commute. Right? So different modes are independent degrees of freedom. So I should say here, now we have quantum modes, or you might say quantum waves. But we also have quantum particles, which are associated with excitations of the field, the quanta of excitations of the field. And we might talk about the momentum of the photon. But that's not this. It's a different deal. That's something else. Think about that a little bit. This P is not the momentum. This was the quadrature of the mode, not the momentum of the photon. I'll let you guys think about that. All right. Now, an important, if we're trying to kind of try to distinguish, as we are, what we mean by classical versus non-classical light. Let's see if this actually does anything.
It makes a sound.
Okay, we'll see what else it does. Then we want to categorize certain states of the quantum field as quasi-classical, right? And what properties those might have. And as we remember, those states are what we call the coherent states. And they are defined as the eigenstates of the annihilation operator. So there would be one for each mode here. Not one, but of course a whole, but alpha here is a complex number. It's continuous variable. Okay. And these have the property, of course, that they are the expectation value of the x and p quadratures are exactly what we expect for that classical amplitude. And moreover, they have simultaneously the minimum uncertainty in x and p equally distributed such that this thing satisfies the minimum uncertainty. Yeah. Okay. Right. So, what we were saying at the end of class last time was that we thus can define, we'll have to think about what this means more precisely, other than a definition. As classical light are, or I should say quasi-classical light, are those states which can be expressed in terms of some statistical mixture. Now I'll allow arbitrary number of modes. So I'll use a kind of, this really means dx1, dp1 times dx2, dp2, et cetera, times some probability distribution times some projector. So this, what I mean by that, this state here is meant to be a shorthand for having a coherent state for mode 1, a coherent state for our mode 0, mode 1, etc. And that's what I mean by it. That's just my shorthand for writing that. That's saying every mode of the field is in some coherent state. So this is a pure state. And now I allow myself the possibility of having a statistical mixture of those pure states with some probability distribution that's associated with each of those amplitudes. Yep.
Does P also have to factorize, or is that?
No, that's not necessary here for this. I could have classical correlations, right? And that certainly can be true, and that is true sometimes. The way in which one mode oscillates can be correlated with the way another mode oscillates, but the way in which those correlations are is purely classical, in the sense that it has a description in terms of classically unknown hidden variables. Okay, so that's certainly fine. Okay, so states of that sort are the thing where this function is positive or non-negative and normalizable. Okay, then we would call it a classical probability distribution. So let's just quickly look for a phenomenon. What if the state is restricted to this class? Then that limits certain outcomes of measurements that are possible. Okay, some things that we might measure might not be describable by states that satisfy this property. So let's look for an example. Let's consider a single mode, just for simplicity. So I'll just simplify my notation, write it like that. And let's ask ourselves, what is possible in terms of the fluctuation if we were to have a photon counter? So let's consider photon counting. So we send this light onto some detector which counts photons and sends out some spikes that counts photons. Okay? And I want to know in a certain time interval, which would correspond to this mode, what are the fluctuations that I expect or are possible in terms of the number of photons I can count, how much statistical fluctuation is possible. So let's ask ourselves, what is the fluctuation then? Well, that's equal to the expected value of n squared minus the expected value of n squared, right? Which is equal to the expected value, I'll write it this way, the trace of rho with that operator. That operator is A dagger A times A dagger A. Minus the trace of rho with A dagger A squared. I think I know I knew a lot of shock. This will be a theme for this semester. All right. So how am I going to calculate that? Any suggestions?
Put in the expression for rho.
Uh-huh.
The trace will make that into an inner product, and then you can.
Right. Exactly. So now what we see here is that when we look at let's just do a little aside over here because I want to emphasize a particular point. So let's suppose I consider any observable, which is a function of A and A dagger, and I look at its expectation value with respect to a state of that form. As Keith suggested, if I plug that in, and then I use the famous trace takes this to this rule, right? Everyone knows that's the make the noise and put it together. That's equal to that. Right? Okay, now using this, which was very cleverly not erased, and the fact that A acting on the ket gives me the eigenvalue, and A dagger acting on the bra gives me the complex conjugate of that eigenvalue. amplitude, then the way to calculate such things is to reorder it through commutations, put it into normal order, as we call it, putting all the A daggers to the left and all the A daggers to the right. So with that in mind, if I look at this again, right, this is of course already in normal order, but this is not. So I can get it into normal order by a commutator. So I'll do that. This should be squared, pardon me. And that becomes then A dagger A dagger A minus A dagger A squared, and then I have the leftover term, which is plus A dagger A. Okay. So we ended up in this expression for looking at the fluctuation with an extra term that came from the quantum fluctuations, let's say, the thing that had to do with the commutation relations. Now these things, when we use that, this is going to be equal to the average of alpha to the fourth, right, minus the average of alpha squared. Okay, now just write this plus the average n, which came from the quantum commutations. So these terms are coming from the fact that the system might be a noisy field. It might a classically noisy field. This is equal to the average of alpha squared, where this average is related to averaging over the probability distribution minus the average of alpha squared plus n. And this is what let's say. Now, summarize and say what we see is that n squared, average of n squared, is equal to the fluctuations in the mean squared amplitude plus n. So, if I have a coherent state, well, before I say that, what can we say about this? That is certainly a positive number, right? Because it's the fluctuation of a positive quantity. This quantity is always positive. So this has to be greater than or equal to 0, which means that for quasi-classical light, the fluctuation in the number of photon counts in a given time interval, time mode, must always be greater than or equal to the average n. Okay? And the equal is in what case? For a coherent state. That's when I have no fluctuations in this amplitude. When that, you might say that probability distribution is a delta function, right, at a particular value of alpha. So for a coherent state, we have the fluctuation equal to n, and that is the case of Poisson fluctuations. But if the light is classical light, then we must have super Poissonian. That is to say, the fluctuations in n must be more than n. If we see sub-Poissonian fluctuations, if the fluctuations in n are less than, or the fluctuations squared are less than n, or the fluctuations are less than the square root of n, that's impossible for classical light. But it's not impossible for quantum light. Of course, what that means is that quantum light must be, if it's expressible this way at all, and we don't really even know whether that makes sense mathematically yet, it would have to be that this function is negative in some way. Because if this function were negative in some way, well then, this could be negative. It's the only reason this is necessarily a positive number is because this was a positive function. Okay? So if we see, so one signature of non-classicality is sub-Poissonian statistics. Yeah, so you get a question.
Is this related to when we have those like bigger functions that have like negative?
Yep, indeed.
Okay.
And we're going to talk about that in a few lectures. But this was an example, not about the Wigner function. Well, we're going to get to that very soon, and the subtle differences between the Wigner function and what we call the Glauber P function. Okay? And what's the difference between them? You know, maybe we know, maybe we don't. But what we just saw here is that sub-Poissonian fluctuations necessarily imply non-classical light. That is equivalent in this case to saying that the P function is not positive. All right? So that's an example of a non-classical phenomenon. Now what about the Poissonian fluctuations themselves? When I'm exactly Poissonian. Well, you know, we express this here. This came from, in this case, the situation where we looked at this in terms of a quantum field. And we saw that this extra n here came from the commutation, the lack of commutation. I mean, you can think about this expression as that there are two contributions to the fluctuations that we see on this photon counter. One is coming from the fact that they're particles, and because they're particles, there's some notion of randomness that we'll come to. And then there's kind of a wave randomness on top of that. And the two combine. Actually, I learned recently, actually Einstein sort of saw this right away when he was looking at Bose-Einstein statistics. And he made, in one of the early papers in the early 20th century, talked about it this way. We'll see a little bit of that. But what about these number fluctuations, this part? I mean, this is a picture in which we imagine the Poisson fluctuations, where we said we had a kind of perfectly well-defined coherent state, but nonetheless, this photodetector gave random clicks along the way with some fluctuation. Well, where are that randomness come from? Well, we can think about that in terms of a stream of particles that are kind of coming along in random ways with Poisson. And that's the kind of, this noise of random particles hitting a wall is what we would call shot noise. We discussed last year, and I know everyone remembers everything we discussed last year, one really doesn't need to invoke the quantization of the field in order to describe this random process. That's to say, this we thought about as, there's a photoelectric effect happening whereby electrons are ejected when they have energy above the work function, and then they get collected and amplified and so forth and so on. So that's a picture of the photons, but really we don't need to quantize the field to describe the photoelectric effect. As we remember, if we thought about it, okay, there's some ionization potential here. Here's if my energy is above this amount, then the electron is ejected. But I can describe that absorption process in terms of quantum matter plus classical light. Where I think about this, for example, as an interaction of the electric dipole moment associated with this material, which is a quantum degree of freedom of the material, and then there's a classical field, say some, And because if I just looked at Fermi golden rule and said that there's a random process of a quantum jump happening, I will get the same statistics. Now, it matches exactly, and it's something I've never completely understood, and one day I will when I finish this damn book. Why, though, these two pictures absolutely jive by writing down something that was an eigenstate of the annihilation operator, I recover, which happens to have the Poisson fluctuations. I recover this exactly. There's something deeper there that I haven't yet understood. But the point here is that when we talk about the classical light, we can talk about that just in terms of the classical statistical theory of classical waves plus Poisson random absorption. And think about that Poisson random absorption as coming from something about how the quantum matter responds to a classical field. And it'll give me exactly the same results. But if I see sub-Poissonian statistics, there's no way to mock that up in terms of classical matter with the So that means that to really try to get some of the distinction between what we mean by quantum light and classical light, we want to, what Glauber did, Roy Glauber, the sort of godfather of quantum optics, is formulated the problem in terms of a quantum theory of photodetection, which involved the quantum light as well as the quantum matter. Okay? And we talked about that last semester. I just want to highlight a few points here so that we have a launching point as we go forward. But, the Glauber theory of quantum coherence had at its heart said, well, if I'm going to do that, I'm going to have a quantum description, a photo photon counting. And we don't have time to redo the whole lectures again, but let me just remind you of some of the key essence of it. Okay, so if I just use Fermi's golden rule, what Glauber showed is that Fermi's golden rule, if I had a photodetector that counted individual photons, using Fermi golden rule, what he found was that the rate of detection was proportional to what you might expect. I start with some, I'll think about it as a start, just as for simplicity. There's some pure state of the field. And I absorb a photon. And then I look at the magnitude of that square. That's what you get. So it's related to what you would expect. The expected value of the number of photons in the field. Okay? Or more generally, it doesn't have to be a pure state, it can be a mixed state. I'll just call it the expected value of a array. Now, if I have multi-modes and I think about this as a field, then as we described last time, the annihilation operators are associated with what we call the positive frequency component, and the creation operators with the negative frequency component. So this, what Glauber wrote down really was this. And so this is what classically we would call the intensity, right? So classically, if I say go back to my double slit type experiment, I thought about light incident on this screen, it responds to the intensity of the light. I'll see some pattern. So classically, I would have the intensity, you know, as of say, it's a function of position, for example, which would be related to the square of the complex amplitude, or E star E. Right? Quantumly, we get clicks. And the rate at which we get those clicks are related to this, which is the quantum analog. So sometimes this is written as the intensity operator. The intensity operator here is written with the negative frequency components on the left and the positive frequency components on the right, because it's normally ordered in that way. That's where it came from, because we absorbed a photon. Okay? Now, the interesting thing comes in when we start thinking about correlations. So as we looked at the Hangel-Mendel in the first lecture, but one of the most important that sort of led to the whole theory was Hanbury, Brown, and Twist. Hanbury Brown is one person. Twist is the second person. Where instead of looking at the intensity at some point, they looked at the correlations between intensity. For example, in order to, let's come back to this board, the say spatial coherence of this wave we're seeing by the fact that these two spots give rise to waves that interfere with one another. And if there's a certain coherence area or length to this, if I move those two pinholes too far apart, then I'll stop seeing interference here. And that interference is being seen here by looking at the correlation between the electric fields that interfere to give this final intensity. But in a particular application, Harry and Smith were actually radio astronomers. They were saying, well, instead of looking at two pinholes and then interfering the fields, let's just directly detect the intensity with antennas. They were looking at, in their problem, the coherent size of stars. So I get some intensity at position 1 and some intensity at position 2, and then I'm just going to multiply them together and average. So it's a correlation between intensities. Okay. To try to measure the coherence of a star. Now, this caused some confusion here because they were seeing coherence by correlating intensity rather than correlating fields. And each one of these corresponds to, you know, from the quantum perspective, if I see some intensity here, it's because a photon was absorbed at this detector, and intensity here, a photon was absorbed at this detector. And as we said, the great Dirac said, photons only interfere with themselves. They don't interfere with other photons. So how can I measure coherence by looking at something having to do with more than one photon? Well, now we know, because really it's interference of not the individual photons necessarily, but the history of. So there might be two different paths whereby the star sends one here or here, but you don't know which one it was, and they can interfere. But what is the quantum description of that? Well, the quantum description of that, according to Glauber now, I have, say, 2 photon absorption. So loosely speaking, I'll use the same quick hand waving, super quick, you ready? We have Fermi, golden rule, which says that this 2 photon absorption process, the rate of that depends on absorbing 2 photons. So that's 1. Okay? And that is the expected value of A dagger A and the A. And that, when I go to the field description for, say, these 2, and I forget about the polarization, click there or not, there's an A dagger for R1, an A dagger for R2, an A for R1, and an A R2. Now this is not the same thing as the intensity at R1 operator times the intensity R2. Why? I can just plug in, I wrote down, this is my intensity operator. I plug it in.
It's the normal order.
Because they don't commute. Right, exactly. If I were to plug this in, I'd get, you know, E minus R1, E plus R1, or, you know, E minus R1, E plus R1, E minus R2, E plus R2. And E plus and E minus are like A and A dagger. They don't commute. So that's not the same thing. But what this is equal to is this. Now, what the heck does that mean? So this is the notation we use in field theory all the time. This is what's called normally ordered. So there's a little bit of confusion here, and I want to try hard to explain the difference between what we just did at the beginning of this lecture, where we commuted things and put all the A daggers to the left, all the A daggers to the right, and the normally, what this symbol means, this double dot symbol. What this double dot symbol means so let's look at that particular case. Normally ordered means, forget about the fact that they don't commute. It's all, whatever, how many A daggers there are, put them on the left, and however many A's there are, put them on the right. Okay? That's what that means. Right? So we would say, for example, n squared is equal to the normally ordered form of n squared plus A dagger A. Okay? That's what that notation means. So when we say put it in normal order, we mean different things in different contexts, and it gets confusing. So, but this symbol has a definite meaning. It means forget about the commutation functions and put all the X's, all the A daggers on it. However many there are, put them on the left, and however many A's there are, put them on the right. So that's what this is. Okay? Now, with that, yes, sir.
So aside from being a convenient shorthand, that allows us to make equality statements and whatnot, what do we actually use this for?
Right, so the point here is, and that is the following. Why would I introduce such a notation? Well, because what Glauber says is that an endpoint joint or coincidence detection of photons is equal to this object. Okay. It's not equal to the, just to part it out, but the normally ordered ones. Now, suppose that the state of the field was a coherent state, a perfectly coherent state. With as many modes as I like. And now I ask you, what is this equal to?
Is it E minus 1 through n and E plus 1 through n?
Yeah, exactly. So let's look at it. Let's look at the particular case. Let's look at what's called the G2, R1, T1, R2, T2. Okay. That's equal to, I put all the E minuses on the left. Of course, all the E minuses commute with themselves, and all the E pluses commute with themselves. So it doesn't matter what order I put those in. Okay, that's what it is. So, what happens when E plus, this operator acts on that? Well, E plus itself, which is a superposition, let's just remind ourselves here, E plus at R at T was the sum with some, you know, square root, blah, 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 a, this is e minus, or e plus, sorry, aj e to the I omega aj psi omega j times whatever the mode function. Right? That was our positive frequency component. So what happens when that acts on the coherent state? The A gets fixed by alpha. So the coherent state is an eigenstate of E plus. And its eigenvalue is just the classical field with that classical amplitude. And this then acts on it. It is also an eigenstate, replaced by the eigenvalue that just takes the hat off. I do that all the time, every morning. What about these guys? It's exactly the same thing. I mean, this is what we just did in terms of we had the A daggers be there and the A's here, and they each one got replaced, but now just in terms of the whole field rather than just a single A or A dagger. So by having it in normal order, the expectation value of the normally ordered product, if it's a coherent state, just gets replaced by whatever that complex amplitude is associated with that coherent state. Or said equivalently, it's the intensity at R1 times the intensity at R2. Maybe you have time in there as well if you like. Too many things to write. Okay. So if I have a coherent state, the average rate of detection of photons I see is exactly what I would expect from the classical. Exactly. And for no matter how many joint detections, and the coherent state is the unique state that does that. It shows what we call nth order coherence, because no matter how many of these things I had, because of this normally ordering, I put as many that E pluses over here, and the E minuses over here, and each one would be replaced by its own wave amplitude, and I'd get just a product of those intensities. And if the state is a statistical mixture of coherent states, with some classical probability distribution, then what can I say about, say, this G2 correlation function, for example? Well, it's just going to be the statistical average of these, just as Hambury, Brown, and Twist wrote down. So if the state is quasi-classical, I would just get what I expect from the quantum theory would exactly predict the same as the classical theory. And if there is finite coherence in the waves classically, that would show up in the quantum theory as well. Okay? But there are some correlation functions which can satisfy certain inequalities that can be violated when the state doesn't satisfy this property, as we just saw. We saw that if we saw sub-Poissonian statistics, that is not describable in terms of either the fully quantum theory or the classical theory if the quantum theory is restricted to states where this is positive. So one example we saw is Self-Personian statistics. Sorry, over here. Another thing you can prove to yourself, and we did this last year, is the problem of photon bunching versus anti-bunching. So suppose we take light, collimate it, and put it on a beam splitter. Okay? And we have the two detectors that are on this, up each side of this beam splitter. And now I put a little delay line here, and then I look for coincidence. Okay? So I'm counting individual photons. Each one of these things is a single photon detector. I'm looking for the situation where I have two photons that are separated from each other by some time tau. Okay, when tau is 0, they come together. If tau is bigger than 0, they're coming apart. Classically, what we would do is we would just take the intensity, turn it into photocurrent, and then just multiply them together. So classically, this is the correlation between the intensity at that position at time quantum I look at the normally ordered product of this. Now, again, if I have a state which is a statistical mixture of coherent states with a classical statistical mixture, I can say something about this. This is like an inner product between two functions. And I can use the Cauchy-Schwarz inequality to say that this must be greater than or equal to the square root of this squared times that squared. Because when I'm looking at the product of two functions integrated over a positive function, it's like an inner product. It's like the dot product of two vectors has got to be hold on a second, to be smaller than bigger than.
Probably smaller.
No, this is the other way around. Right. The dot product's always smaller than the length. Yeah. Okay, so if I have, for example, stationary light such that the fluctuations in the intensity are the same at any time for stationary light, this would just equal to the average of I squared at any time, either time this time or that time, right? Either tau or 0, if I have stationary light. So this is the related to, from the point of view of the quantum theory, that's that object. This object is related to the joint detection t equals 0 and t equals tau, whereas this is joint detection t equals 0 and t equals 0, both of them coming together at the same time. So, if the light is classical, then it must be the case that the correlation, the chance for the rate at which they come together is always bigger than the rate they come apart. So classical light is what we call, it's bunched. The photons are bunched together. They're clumped. If we see the opposite, that's a smoking gun of non-classicality. If we see photon anti-bunching, the photons are somehow separated from one another. The chance for them to come, the chance for two photons to be together is less. That cannot be described in terms of this is right. Okay, so the upshot of all of this is that we have a way of distinguishing classical from non-classical light in an operational sense, right? That is to say, we think about here in the Glauber theory, we're talking about counting photons. And we have a fully quantum theory of how what we expect the photon counting rates and probabilities to be. And there are certain phenomena that are completely describable in terms of the classical theory when we take that classical theory in terms of the coherent states and statistical mixtures, right? Anything that violates the inequalities that follow from that ansatz, we call non-classical. But it's tied to this specific kind of experiment where we're counting photons. Keep that in mind. Yes, sir?
What kind of time frame determines bunched versus anti-bunched?
Yeah, that of course will depend on the spectrum of the light. So you may remember if we looked at this kind of experiment and say we looked at what's called the little G2. You'll see this in literature all the time. I'm sure you do. If you work in this area, people talk about the G2. This is the G2, the big G2, divided by G1 and 0 squared. So this is sort of related to the ratio of these two guys. If I look at this, what I find is the following. If I have a coherent state, G2 of tau is 1. Okay? That's to say, I have complete uncorrelate. There's no correlation between this Poisson. There's no correlation. That's not bunched, it's not anti-bunched. If I have natural light from our light bulb, what we see is this. And the width, which was your question, over what time scale over here, is related to the spectrum. So the coherence of this light is measured in the width of this bump. That was an example of, again, measuring coherence in a light wave by looking at a correlation between two different photons. And if I have, so this is bunched, this is classical light. And if I see the opposite, anti-bunched. So often people, when they try to, say, create single photon light sources for applications, they will do this kind of Hamburg-Brown twist turn and try to see that it's really a single photon. Because if it's a single photon here, well, then it can't come be at these two places at the same time. It would have to come at a later time. You wouldn't see two bunched together. All right, very good. So what we just talked about was a review from last year when we had quantum optics 1 as a way in which we distinguish classical versus non-classical in certain phenomena, and that was related to, in the Glauber theory, to photon counting and the discrete variables. Okay, so the Glauber theory distinguishes classical from non-classical light in terms of photon counting. And what the upshot of all of that was that classical means positive P representation. If you have a positive representation, then we can explain these photon counting experiments totally in terms of classical waves and plus the shot noise that we throw in there as an essential feature of the absorption process. Okay? But this counting, photon counting, is a discrete variable. As we discussed a little bit last lecture, we can think about the field in terms of the particles, the photons, or we can think about it in terms of the waves. Something that, instead of detecting the quantum particle, detects the quantum wave. Which leads us to another notion of classical versus non-classical light. Particular the quadratures, instead of thinking without the photon numbers n. So to get into that in the last few minutes, I want to review some more of the properties, the mathematical properties of coherent states and quadratures that we discussed last year that are going to be essential mathematical machinery that we're going to use throughout the semester. Okay? So let's just do a quick more review of coherent states and continuous variables. Which in modern quantum optics are called CV. Why? Because they use a continuous variable. Okay, so let's recall some things. Again, we had that our coherent state was an eigenstate of the annihilation operator, and had the property that its expectation value had the expected form. So when we drew this picture, we said in phase space, we thought about the coherent state as having, being a wave packet localized at a point, or center was at the point, and then had some fluctuations around that, right? So the fluctuations in this, as we said at the beginning of the lecture, were both equal over 2. This state is in fact a displaced version of the vacuum. So the vacuum, of course, is an example. The state of the field with no photons is an eigenstate of the annihilation operator with eigenvalue 0. It is a coherent state as well, but with 0 amplitude. So this is 0, and this is alpha. There is thus a unitary transformation that maps the vacuum into alpha. This is what we call the displacement operator. It's a unitary operator that maps one quantum state into another. What is that operator? Well, it displaces something in X and in P simultaneously. Remember, of course, that momentum operator is the generator of displacements in position, and the position operator is the generator of displacements. Wait a second, I said that. The momentum operator displaces in position, and the position operator displaces in momentum, right? So I can think about d alpha. It's a function of those two variables, this coordinate, xp coordinate here. That's my alpha. Alpha is x plus as something that displaces in. So the thing that displaces in position is the momentum operator. The thing that displaces in momentum position operator, they don't commute, but I can write it in a symmetric way by putting them both in the exponent together. That's my definition. Okay. Let's see that in fact, so if I were to rewrite x and p, where alpha is x plus ip over root 2, and the annihilation operator is x hat plus ip hat over root 2. Plug that in, I get e to the alpha a dagger minus alpha star a. Okay, little algebra. I claim that if I look at A acting on alpha, which is that, I get that. How can I prove that? Well, one way to quickly do it is to stick in a d dagger. Clear that this operator is unitary, right? It's e to the I with the it's e to the the anti-Hermitian operator. The initiative of the anti-Hermitian operator is unitary. So I can do that. That then is equal to D dagger A, D alpha 0, right? And what's that? Well, how are you going to do that? Let's just quickly remind ourselves of the last thing we do. That's a unitary transformation acting on an operator. How do I do that?
I'm halfway tempted to commute A and D.
Right, I could certainly do that. And then how would you do that?
It would involve understanding how to expand that exponential.
Yeah, that's right. So to do this, you use what everyone absolutely remembers, Baker-Campbell-Hausdorff, right? Which says, Baker-Campbell-Hausdorff says, e to the A, B, e to the minus A is B plus the commutator of A with B plus a half the commutator of A with A and B plus etc. Right? That's how you do that. When you do that, you get the commutator of this with that gives me alpha. And then the rest of them, everything else commutes. So this becomes, is equal to, so let me write it over here, d dagger alpha A d alpha is A plus alpha. So, I then plug that in. A acting on the vacuum is 0. Alpha pulls it out, and this becomes alpha d alpha. Times that, which is that. Now I can draw this with a beard. That's the smiling face guy with no hair. Maybe get a beard just like. Look like Santa. Terrible. All right. So a coherent state can be written this way. It's a very the displacement operator is going to play a starring role here. Let me just quickly write one last thing. We also know we can write using variance on Baker-Campbell-Hausdorff, e to the A plus B can be factorized as e to the A times e to the B times e to some power of a commutator if A and B commute to then give me something that commutes with these guys. So this thing equals e to the alpha A dagger e to the minus alpha star A times e to the minus the commutator of alpha A dagger with minus alpha star A with a half in there. Minus a half of that. And this is equal to e to the minus alpha squared over 2, the commutator, I got it backwards, and there's no minus sign there. That's a plus, pardon me. Minus alpha squared, A dagger.
Oh. Should be a minus outside probably.
No, it's got to be there, right? Yeah, no, this one was there, that becomes plus. Right, okay, this is correct. That is correct. And that is What is A dagger with A? What's the commutator? -1. So this is equal to e to the minus alpha squared over 2 e to the alpha A dagger e to the minus alpha star A. So, with that said, D acting on the vacuum is equal to e to the minus alpha squared over 2 e to the alpha A dagger e to the minus alpha star A acting on the vacuum. Okay. Now, what is this acting on the vacuum? Well, I expand this as a power series. Acting on that, n equals 0 to infinity. And what do I get? 1, right? Because the only thing that every other term where n beyond n equals 0 annihilates it. So I can replace this by e to the 0, which is 1. Then I have this guy. What is that? Well, when I operate the creation operator n times on that, of course you remember that n is equal to A dagger to the n on the vacuum divided by square root of n factorial. Right? So that means that this coherent state, alpha, is equal to sum n equals 0 to infinity, e to the minus alpha squared over 2, alpha to the n divided by the square root of n factorial n. Which is what we wrote down last time. These are this is the probability amplitudes for the expansion of the coherent state in terms of the Fock states, such that with the probabilities, it's Poissonian. Okay? So the displacement operator is your friend. Learn the displacement operator. We're going to have lots of practice with it in homework, and we'll be covering that one. All right. Thanks for bearing with us for a little extra time. We will pick this up